will be chapter 24. So what are you going to expect? We have now this one here, your principle of virtual displacement, PVD. So you have an explanation there in Mechanics 3, but what I'm going to do is present first some theories or some basics. So this one is principle of virtual displacement. So it starts from this equation going here and then here at least a bit, just to be able to come up with this stiffness matrix equation. Yes? So there's a lot of steps, but what we're going to do is I'm going to start with a bar and a beam again, and then hopefully by next week we will be able to solve, or we will be able to discuss this derivation and solve some examples. So once you get this one really, K equal to the volume integral of BE dt dV. So this one is very similar to a bar. Because what we're looking at this one is that your plate will be linear. So it will be displaced in a linear manner. Or response will be in a linear manner. So as you can see, because it's a plate, it's not dx, it's dA. So now you're going to integrate with respect to x1 and x2. And then from here, because you cannot determine the values or the symbolic values, you have to integrate numerically. So this is what we can get for a bar, but this one is different from, but what we can get for a plate will be like this one. No, I think you cannot simplify this one anymore. This one is the simplified version. And then your stiffness or your strain displacement matrix can be determined using this one here. So as you can see, you have a lot of shape functions there. N1, N2, N3, and 4. So 4 shape functions. And then your Jacobian will be a 2x2 matrix. Yes? So to be able to go to that level, let's have a look first at your principle of virtual displacement using a bar. So please bear with me for this one here. It's a bit tough to handle this one. But since we're going to use this one, we're going to use the same principle for a beam as well as a plate. We probably have to just discuss it anyway. So just accept whatever solutions that came up here. This one is very simplified really, but just try to accept. So let's have a look at this one here. We have discussed about your stress strain curve already. But for linear finite element, we're just looking at this linear. So take note, we have already back in your continuum mechanics, so you have this one for your stress strain curve. But for linear finite element, we're just going to use this section here. Yes? So this is what we're going to do here in linear finite element, we're just going to consider that elastic region. So that what's going to happen is that we will be limited to this area alone. Yeah? So, this area here, if we're looking at the force, displacement, stress, strain, for the triangular area under the linear elastic graph, we have 1/2 F multiplied by that. So that will be the area under this elastic curve. Yes? So you have this one in Moodle. So similarly, if you're looking at stress, the strain energy will be that area under this line here. So all that area there, strain energy. So your strain energy will be 1/2 stress multiplied by strain dV. So that is your area. So you move this one to this side here, and then remove the half, then you have now this one here. For a multiple or multi-degree of freedom problem, you have now here the transpose of your force multiplied by that displacement minus the strain energy, or twice the strain energy, that is equal to 0. So this is now your equation, which has been derived from the elastic stress strain curve. Virtual displacement. So this virtual displacement is, we assume that there is a, so we have a force, just apply a force, just a bit one, so we will have a very small virtual strain. So this one is a very tiny strip, rectangular in shape, but very thin. So that displacement here, because the axis here is the displacement, so that will be a virtual displacement. Just a very small displacement, no change in the force or whatsoever, just apply a small virtual displacement. So that this virtual displacement with a V there is equal to, or virtual strain, that is, sorry, is equal to the derivative of that virtual displacement with respect to x. So no change, it's just that we have the virtual sign there. So your work done virtual will be equivalent to that force vector transpose multiplied by your virtual displacement. So the same, we didn't change any equation here. We just put there the virtual sign there. So your virtual strain energy will be equal to the stress multiplied by the virtual strain dV. So we have now this one to be equal to this. We were able to prove that earlier. This is equal to that, just remove that. Fu stress strain. So you have your work done equal to the stress strain energy. This one is equal to 0. So you have now your virtual strain, or your virtual equilibrium condition, or sorry, constitutive equation. So you have now that. So just bear with me, no change, it's just that we have there a virtual symbol. So you have now your constitutive equation, just repeating what we got. So you know that your stress is equal to E multiplied by your strain. So it's just expanding now. So this is your force multiplied by your virtual displacement minus that stress strain. But stress is equal to the modulus multiplied by the strain. So you've now got this equation here. So let's look at E power element. So we know that this one is a strain equal to B transpose U. So we were able to get this one earlier already. Yeah, so let's do this one step by step. So we have now your strain equal to this equation. So we're going to put it there. So what happens now? So once you have this one, put it there, so you get now this one, and here, instead of that, you use virtual displacement, so you get now this one here, where that is now your virtual displacement. So no change. So as you can see, no change. So F multiplied by U, force distance, that is your work, and this one is your strain energy, stress strain. So because your stress is equal to this one here, and this one is equal to that, then you can simply substitute it to get this equation. Rather straightforward substitution. So the thing here is, how do you get that virtual displacement matrix? So the challenge here is getting this virtual displacement matrix. It's actually an identity matrix. Depending on the degree of freedom, then that will be the size of your matrix. So for a bar, we have 2 nodes, because we have, 1 DOF per node, so we have 2 degree of freedom. So we have a 2 by 2. So 2 by 2 displacement matrix, or virtual displacement matrix. So just bear with me with this one. So this, we know this one. This one is that, so we just added some virtual. But what is this virtual matrix? That is simply an identity matrix. That is simply an identity matrix. So if you try to look at this one here, same, force multiplied by the virtual. I would like to go back. So this one is an identity matrix. So have a look at this one here. Your virtual displacement is just an identity matrix, and what is the size of your identity matrix? This will be dependent on the number of nodes per element. So in this case, you have your identity matrix to be 2 by 2. Now let's have a look at this one. What will happen here? So here, this one is just an identity matrix. So just example, you have a force. So you have your force is F1, F2, let's say. Yep. And then you have now your virtual displacement to be, say this one now will be 1, 0, 0, 1. So let's try to multiply that. What do you get? So you have F1 yes. So this one is 1. This one is 1 by 2, 2 by 2. So what's the size of our matrix here? 1 by 2. Yes. So this one is simply, that's F2. So what do we get? So this one is simply F1, and so F1 multiplied by 1, F2 multiplied by 0, that's 0. So F1 multiplied by 0, F2 multiplied by 1, we get here F2. So what can you say about this one here? So this is the same, yes? This one is simply F transpose. Reason, because you simply multiply this one with 1. An identity matrix is just simply 1. So let's have a look here. So this one now is equal to 1. So force transpose, we've done this one already. Okay, and this one is just an identity matrix. So that is just an identity matrix. So it's just multiplying this one with 1 and multiplying this one with 1 again. Yes? So we have now this one here, this multiplied by 1. So what happens? So that is just that. And this one without this one is this one now here. Okay? And then we can now bring out this displacement somewhere outside. So we can bring it outside. Or, no, sorry, we put all of these to one side. Let me just write. Yes, so what happened here is that if we want to get our f, say for example, the thing that we wanted to do is f equal to k multiplied by u. So the target here is determining this value here. So with this virtual displacement, we want to get an expression for k. So that is now f transpose, and then this one here. Now, have a look at this term here. So this term here, ui, is equal to, that will be b1, b2, and that will be u1, u2. So that will be b1, u1 plus b2, u2. So it's just a scalar value, yeah? So if you inverse a scalar value, or take the transpose, what will happen? Still a scalar value, it's the same value. Scalar. So to be able to get this force here without the transpose, so we need to inverse, or we need to take the transpose of both sides. Yes? Take the transpose of this one, and take the transpose of this one here. But this one is a scalar, so if you transpose a scalar, it's a scalar. If you transpose this E here, it's still E. But if you transpose B transpose here, then it will be B. So what will happen is that once you transpose everything, that Fi is equal to the volume integral of dE Yes, so we took the transpose. This is a scalar, so just consider it to be a scalar. So when you transpose it, it's still a scalar value, no change. But this one is a matrix. If you transpose the transpose, that's simply equal to B. So there you have it. So you have now this value here. Okay, so you equate them, F equal to this one, B transpose dV. You take the transpose. You change that, take the transpose, what we have, BE, BTU, still the same, no change. And then after that, bring this one out, bring this one out, you get now your BE, BT, dV multiplied by U. So we have now F equal to K multiplied by U, where K is the volume integral of BE, BT, dV. So that's one way of determining your stiffness matrix for a bar. So there are many ways to skin a cat, so this is just one of them. The other one is the method of weighted residual. So what did we present earlier? So what are the methods that we used here? The first method that we use will be that method of weighted residual and your Galerkin's method. Yes? And then the current one that we discussed is the principle of virtual displacement. Yes? The thing is that if we're going to a more so-called more advanced element, you cannot use this method anymore. You can use this method to be able to obtain this one here. So for example, we want a beam. We cannot use this method. We can only use this one here to be able to get an equation for your stiffness matrix. Okay, this one is already complicated, so this one is just a bit more. It's a bit complicated. So again, once you get this one, you're not finished yet, right? Because you need to have your shape function. And once you get your shape function, you take the derivative, put it here, perform the necessary integration to get your to get your stiffness matrix. So again, as you can see, finite element method is just procedure. So you memorize that procedure. You don't memorize those equations because really it's so difficult to memorize these equations. So you just take note on the procedure of finite element. Questions, anyone? We're going to meet this Thursday, yes? So let's meet. What was the time? Is it 9 or 10? 10 o'clock. Okay, let's have 2 hours, 10 to 12. I'll arrange the room and I'll inform you about the room. I would like to, once having all of these, I'd like to have a lot of tutorials with you guys. Yeah. Well, this one is again something for the beam. Yes. Take note. The strain for bar is simply straightforward because that's simply the elongation divided by the original length. That is the strain. But for a beam, you have now this y divided by this rho. What is rho? That is the inverse of the curvature. So that makes a bit. That makes this equation a bit more complex as compared to a bar. So all of this flexure formula you should be familiar already. Moment is equal to this, equal to that. Normal stress bending, M equal to my all over I. Sigmas equal to my all over I, where I is equal to the second. The integration of that y squared dA, the integral of y squared dA. So all of these has been presented before last year, but just to have a look, this is how, just to have a review, these are the terms that you should be familiar with. Strain, stress, moment, and the second moment of area. So these are the things that you must be familiar with when it comes to beam. So we've done this one, we have boundary conditions, so there you go, PVD. So, again, it's the same, we have the equation, it doesn't change. You have your force multiplied by the virtual displacement minus stress multiplied by the strain. So no change here. Yes? So again, you can expand this one, stress equal to modulus multiplied by the strain to get this one. Your question here now is, what is your strain? Now, the strain for bar is straightforward. That's du dx. U is equal to n1 x1 or n1 u1 and 2 u2. But what if you have a beam? Your strain is that y all over r, and r is the inverse of your curvature. What is the curvature? Sorry, it's not here. Let me check. Oh, it's not here. So the curvature is that the inverse of the radius. So if you have your beam to be bending, there will be a radius of that bending. So the inverse of that radius will be your curvature. So this is the equation. So I'm just presenting to you just to at least condition your mind later on for a more complicated problem. So as you can see this one there, and your strain is equal to this one multiplied by your curvature. Same procedure, it's just that we have a different value for this one. Yes? So you have now this equation there. Simplify, you have EI, curvature, curvature, virtual, and so on and so forth, until you get this. Sorry. Until you get this equation. Right? So that is now your equation. So what happens here? So for a bar, this is what we can get for a bar. So for a bar, this is what we can get for the stiffness matrix. And then of course you have now your N, and then you have now your B equal to dN dx. So what do we want to achieve for a beam? So you have now your F equal to K multiplied by U. So what is this stiffness matrix? This stiffness matrix is the integral. Take note of this one. That will be your B, EI, B transpose, dx. This will be that line integral. So take note, this will be the change here, wherein you have I is equal to the integral of y squared dA. If you have say a square or rectangular cross section, I is simply equal to bh cubed over L. So this one is your second moment of area. So take note of this one here. So what do we want to achieve here? We want to achieve this equation. So I'm just going to present to you, not too much in detail, but I'm just going to present to you how things are being done behind your beautiful standard equation. So I think I lost my battery there and didn't bring my charger. Okay, what I'm going to do here is just to give you okay. What do we have? So I want you to prepare to search for that shape function. So if this will be your shape function, what will be the shape function How many shape functions do we have for a beam? So for a bar, we have 2 degrees of freedom per element, 1 degree of freedom per node, so we have N1, N2. What about a beam? So for a beam, that is a bar, yeah? What about a beam? So a beam will have U2 at 1, you have your theta 1 and theta at 1, and then you have your U2 at 2, and then you have now your theta 1, 2 at 2. So how many degrees of freedom do we have? 4. How many shape functions do you expect? So you have N1, N2, N3, and N4. Shape functions. So for a bar, it's just that we have N1 and N2. What about for a plate? Just an additional information. What about a plate? So plate, we just assumed a movement here, transverse, but we can simplify this one. We can simplify this one to just 4 shape functions. So we have N1, N2, N3, and 4. So I'm just trying to condition you so that we will be able to solve these problems. So I'll just like to summarize, because I'm dependent on my laptop. So I'd like to summarize what we have discussed. So bar. So you get your. So how do we solve for your? How do we solve for your stiffness matrix? You have your strong form. You have your weak form. Yes. So here you're able to identify the method of weighted residual plus your Galerkin, and then after this one you're going to identify this stiffness matrix, which is B, E, D transpose EV, and then you apply mapping. So you have your mapping from your x-axis to c-axis. So once you do your mapping, you introduce another term, Jacobian. So what is this Jacobian? dx dc. Yes? So you identify your shape functions and so on. You have now your Jacobian and so on. And then finally you come up with your k equal to EAL. Straightforward. Now the other one, of course, is starting with your PVD, principle of virtual displacement. So this PVD will be able to get us this equation only. So take note, this principle of virtual displacement will get us until here already. only, sorry. It will only get us until here. So after this one, you can use now this concept. So your PVD will only allow you to determine this one. So why are we going to use PVD? Because using this equation here to be able to determine the stiffness matrix of a beam, you won't be able to get this kind of form. We need to have a PVD so we need the PVD to get this one here, K, the line integral of B, E, I, B transpose, dx. So we need that PVD to get this one, this stiffness matrix for a beam. But it doesn't end there, because your B is a function of n, yes? dn dx. And for a beam, how many shape functions do we have? We have n1, n2, n3, and n4. So that's why you're going to end up with a 4x4 stiffness matrix for a beam. Okay, so please read up on this one. The slides are in Moodle. I'm going to put it, so please read on this one, because once we move to the plate, I won't be discussing any of this one. I'll just continue the lecture and assume that you have already the background knowledge for the plate structures. Okay, so I'm just going to do that, and please continue on reading. Anyway, it's not a lot, but the mathematics here is a bit tough. So. But the solution is simple, straightforward. Once you know the procedure, it's just an easy task. Okay? I'll stop there. Really, this one is a very boring course. I've seen through a lot of mechanics and finite element courses, and really, yeah, I have to ask myself what I understood after the lecture. Okay, so